Hello and welcome to another video on further maths, and we're tackling a topic on further stats 1. It's called chi-square test. In EDXECEL book, it's chapter 5. So there are two types of questions in this topic, and first is testing if a proposed distribution is a good model for the given data. It's called goodness of fit. And second is testing if two different events or variables have any associations, or these events are independent or not. Okay. Right. So we tackle the first type of question first. There are 4 types of binomial discrete distributions we do in EDXECSEL, especially. Binomial distribution parameters are number of trials and probability of success. Poisson distribution parameters are lambda, mean. Discrete uniform distribution, like the dice, when every outcome has got the same probability, same expected probability. And geometric distribution, we do it only for A2. Okay, so steps to work out these questions, guys. I've just tried to give you some steps here. If parameter is not given already, estimate it, calculate it. Okay, right. So exercise 60, there are question number 3 and question number 4, and we'll be working starting with these questions on this topic. And I'll start with question number 3 of exercise 60. So guys, I've done this question here. I've written this question down over here, and let's see. You could read this question anyway, right? So let me just show that question once more to you. Right, it says, over a period of 50 weeks, the number of road accidents reported to a police station were as shown. Okay, so this is the number of accidents in over a period of 50 weeks. It's number of weeks, that means this total should have to give you 50. I'm sure that does 27, 36, 39. Okay, so 28, yeah, that is 50. Then part A says find the mean number of accidents per week, nothing to do with further stats. Then part B, using this mean and variance of 0.10% of significance level, test the assertion that the data is from a population with a Poisson distribution. That's why we proposed distribution here is Poisson distribution. And we're going to be testing if this is the correct distribution or not. Right, so this is the question we're going to do. We're going to be going over the steps. I'll show you the steps in a minute now, again on the PowerPoint. And then we will go step by step to work out this question for you. Right, so step 1, if parameter is not given already, calculate it. So guys, let's see. The question 1, part A, talks to me about this parameter anyway. It says work out the mean. So how do you work out mean from here is, guys, you do number of accidents 0 times by number of weeks, then plus 1 times 13, and add them all together, then divide them by 50. Let's work out the mean. I'm just going to quickly work that out with you. You can work it out now. Right, so mean comes out as 1.4. This is basic GCSE question. And then we go back and start sharing with you. Right, so second part is using set your H0 and H1. H0 is always proposed distribution good model. H1 is proposed distribution not a good model. So part B of the question asked me to work out the distribution. So guys, the distribution we propose here is, it's a Poisson distribution with 1.4 as its mean. And H0 is always that Poisson distribution is a good model. And which Poisson distribution? This one. And this is, and second one, the Poisson PO 1.4, just write that, is not a good model. Guys, it doesn't change. It always stays the same. This is how you write H0 and H1, always. It doesn't change at all. We show you step number 3. So step 3 is work out probabilities of each outcome using calculator table formulas, then work out the expected frequency for each column in the table. And expected frequency is probability times the total of observed frequencies. So let's see, how do we work out this expected frequencies now, right? All right, guys, what I ask you to work out expected frequencies is you're going to work out the probability first. So probability of x equals 0. So guys, what are we going to do? We're going to be using calculator to go on menu number 7, and it is Poisson PD. So number 2 here. And I will use the list function for some part. Have a look. So I'll use this is 0, 1, 2, 3, and 4. So 0, 1, 2, 3, and 4. And then press equals, you come to lambda equals 1.4. Press equals, guys, you get this probabilities. Okay, I'm going to write this probabilities here on the table. I can do that in the examination as well in the table. Okay, and then we see. So I have noted down all the probabilities from this list on the calculator onto this. Guys, very, very important part I would like to tell you over here, especially for Poisson distribution. Check that does this probability add to give you 1? And most likely it will not, because this is number of accidents and they only stopped at 4. But there's a possibility that you can have accidents which are greater than 4 as well. So guys, that's why you always add another column in Poisson distribution. That will be the complementary event to this. This is up to 4, so greater than or equal to 5 accidents. Okay, and observed of that is 0 as well, no weeks, because 4 is not observed, 5 is not. But you can work out the probability of this. How would you work that out, people? You can either add all of them, then take away from 1, or you can do it again by using 1 minus probability up to equal to 4. Okay, let's have a look now. This is, guys, this is really important part and people do miss it. So what I'm going to do here, I'm going to do Poisson CD, which is number 3. Okay, I'll do variable this time because there's only one number I'm looking for. So x is equal to 4, lambda is 1.4, and this has given me the probability of up to 4. So guys, probability x is less than equal to 4 is equal to 0.98574, and so on. I want to work out probability x greater than or equal to 5 would be 1 minus probability x less than or equal to 4. You've worked that out and you've learned that in a Poisson distribution chapter. So guys, I want to do what? I want to come back to calculation. So menu 1, it's 1 minus the answer, and that gives me 0.0143. 0.0143. This is really important point. Don't miss out on this, people, because your probability should always add to give you 1. Okay. Now, if you look at your step number 3 again, probabilities obviously will help you, but you need to actually work out the expected frequency. So how do you do that? You do probability times the total of all observed frequencies. So guys, once again, let's work that out now. Expected frequencies for all the columns. Right, so here I will advise you to write down the expected frequencies here into the same table if you can. And I did tell people to use different color pen if possible, because what are you going to do? I want to times this by 50 because of 50 altogether. I want to times this by 50, times this by 50 as well. So let's do 1 here. So 0.2465 times by 50, and I get 12.325. So write down here 12.325 is my expected. Okay, 12.325. I'll work out expected for all of them. And okay, so these are my expected frequencies. Okay, now we look at the next step. What do we do in the next step is this. So guys, step number 4 is combine the columns with the expected frequency less than 5. So expected frequency is less than 5. So no column in the new table will have expected frequency less than 5. Okay, be careful while combining the columns. You will need to add observed frequencies as well. Okay, this is really important. I'll tell you what I mean by this is, guys, so I need to see this is fine, this is fine, this is fine because it's bigger than 5. This is bigger than 5 as well. So this is not, we need to combine this. If I combine these two, the total here will also be still less than 5. So that means I need to combine these 3 columns together. Guys, I did say to you, after combining the columns, you need to make sure that none of the columns have in the new table have expected frequency less than 5. So we rewrite this table again and combine this column. This will just write this as greater than or equal to 3. So let me make that table now for you. All right, so this looks like my new table. Look, we just copied only the number of accidents and observed frequency and expected frequency, because these are two things we need to know after that. We need to use after this. And really important, I've just shown here, the observed is 13 at 0 at 0. It's still 13, but I would advise you to make sure that you do add them here. Okay, these are the expected frequencies, guys. Let me check the next step now. So step number 5 is you calculate the test statistic, either using this formula or the second. I prefer the first one. This is just a choice. And use any of the two formula. This is where the mistake happens. So be very careful. What I mean by that is, people, very careful in calculating this. Okay, so let's do this here, people. So what you need to do is, the test statistics is observed minus expected whole squared over expected, then you add all of them together. So guys, that's why it's important to write them in next to each other. So what I'm doing here, guys, 15 minus 12.325 squared divided by 12.325, so plus 13 minus 17.26 square over 17.26. Doesn't matter actually which order you write, make sure that you write this at the bottom, and so on. What will be the next one? This will be 9 minus 12.08 square over 12.08, and plus 13 minus 8.32 squared over 8.32. So guys, put this in the calculator one by one, and this is what I mean by making sure that you don't rush and don't make mistake. And let's work out the test statistic. Guys, this is an absolute choice what you want to do. I've just worked out this one separately. I'm going to work out this one separately, or you can just put this just plus sign in the calculator there, and let's work from there, guys. Plus sign and add another fraction afterwards, bracket on the top. That gives you 13 minus 17.26 squared, then come down or divide by 17.26 and add plus sign again, and so on. This is absolutely your choice, guys. Work that out for me. Let's see if you can match the answer. And my answer comes out as 5.0498 if I haven't made a mistake. So guys, what do? We check the next step after that. We work out test statistic. What's the next step now? So the next step is calculate the degrees of freedom. This is new number of columns in the new table. Take away 1, or another one, take away 1 if parameter is estimated in step 1. So guys, let's see, what do we need to do in this one? Guys, the degrees of freedom, new number of new columns, 1, 2, 3, 4. So be 4. Take away 1. This is standard, but really important, guys. In our question, we did estimate the parameter of this Poisson distribution ourselves. It wasn't given. The mean was estimated. That's why it's take away 1 as well. Okay. Remember, if parameter is not given, you take away 1 extra to work out degrees of freedom. This is important, guys. This is what you need to memorize. Okay. Really important. If parameter was given, then I would have just done number of columns, take away 1. Okay. The next step after that, number 7, is find chi-square critical value from tables. I'll show you how to work out that. Right, so this is the table I'm going to use, which is in the book. What does it need? It needs degrees of freedom, and it needs a significance level. So significance level here was 10. So how do we write this, guys? So, and degrees of freedom is 2. So chi is 2 at the bottom. This is how it's written. And 10%. That's significance level. Let's work out. So 2 degrees of freedom, 10% will that be? It is 4.605. So guys, our critical value for this chi-square for this is 4.605. So what do I do now? I compare, what do we do now, guys? We compare calculate it, which is 5.0498. With the critical value of step 7, which is 4.605. Then how do we conclude? Write conclusions. If test statistics, which you calculated, is less than critical value, what do? You accept H naught. That means proposed distribution is a good model. Let's see what happens in our case. Guys, this is my calculated value. That's my test statistic. So 5.0498, the calculated one, is greater than 4.605. So what does that tell you guys? Just go back and check. What does that tell you? Never mind if you don't remember this, guys. We did say to you, if your calculated value is within this, is less than the critical value, then we accept hatch not, but here it's not. So guys, there's enough evidence. What do we do? I mean, when you enough evidence to reject hatch not, that means the Poisson 1.4 is not a good model. Okay, so that's your first question of the first type. All right, done, guys. We move on to the next question now, which is question number 4, the next question of this. So a marksman fires 6 shots at a target and records the number R of bullseye hits. After a series of 100 such trials, he analyzes his score, the frequency being shown as this. Okay, and it has given you in part B that you're going to be using binomial distribution, so you're not making an estimate in this. Okay, but what you want to estimate is the probability of hitting the bullseye. Okay, so this is we did a Poisson distribution question. Now we're going to be doing a binomial distribution question now. Okay, so let's have a look. How do we start this one? All right, guys, the part A of the question says estimate the probability of hitting the bullseye. This is bullseye. This is really, really important, guys. The estimation, so that means once again, the degrees of freedom when we calculate in the end will be 1 extra constraint here. So degrees of freedom will be 1 less than number of rows, number of columns minus 1. Okay, because we're estimating. But how do we estimate this? With the given data, the frequency and the value of X, value of R, we can work out the mean. Right? And guys, if you know, in a binomial distribution we're working on, mean is actually n times p. Okay, so that is what we'll be using to work out the probability of success in binomial, the parameter of binomial. So guys, can you all work out the mean for me, please? Thank you. We take right. So mean comes out as 2.4. Now, guys, you're going to understand really, really important. There's a big confusion I've seen people do. You're going to figure out what is your n. Is n 6 or is n 100? Okay, there are 2 numbers in there, guys. If you look at the question one more time, and we'll understand what n is. Now look at the question. If marksman fires 6 shots at a target, and this is the result of him or her hitting the bullseye. So of 6. So 0, 1, 2, 3, 4, 5, 6. But then he done 100 such trials. But in each trial, remember, n is 6. Because out of the 6 shots, we recorded the frequency of how many times he hit bullseye. Okay, so n is not 100, n is 6. This is really important that you understand that part. So guys, n equals 6. So we do 2.4 is equal to 6 times p. So p will be equal to 2.4 divided by 6, which is 0.4. That means the distribution we're proposing is binomial 6 and 0.4. Okay, so we need to do what, guys? If you go back to the steps and check, we're going to be working out the probability of each one of them. Okay, and then expected frequency. Probability you can work from the list function of the calculator, and expected frequency you times that by number of trials, which is 100. 100 is the number of trials. This is not, and I mean in this within each trial, n is 6. Okay, right, guys. Let's work that out. Right, so guys, this is number 7 in this calculator. This is binomial PD. We want to work out the probability of each of this. So binomial PD is number 4. List function again, and 0, 1, 2. So 0, 1, 2, 3, 4, 5, and 6. Okay, plus equals n equals 6. That's the model we're looking at. N equals 6, and probability is equal to 0.4 plus equals, and we get this probabilities, because we're going to be writing down these probabilities next to them. Then we times them by n to work out expected frequency. Guys, let's see what the new expected frequencies are now. Make sure that you add the observed frequencies as well when you combine the columns. Okay, so there we are. Okay, the next step is, guys, we need to work out the test statistic. So test statistic is again the same thing. You do expected minus observed whole square, divide by expected, and then add all of them. So people, it's really important for examination, you tell them what you're doing. So I will probably do here 26 minus 23.32 whole squared over 23.32 plus 36 minus 31.1 whole squared over 31.1, at least 2. So show the examiner that I know what I'm doing. You can put that in the calculator and work that out yourself. Okay, I've got that as 3.192. You can check with your answer matches with mine or not. Okay, but this is where the mistake happens of calculation. Guys, the next step is, what do we need to do is we're going to work out a critical value. So x chi-square crit. So for that, we need degrees of freedom. And I did say degrees of freedom. How many are the new columns? 1, 2, 3, 4. So 4 take away 1 is standard. And very, very important, we do take away 1 more, because this time as well, we've estimated the probability, we've calculated the probability. So guys, the final degrees of freedom are 2 one more time, and significance level of the test was 5%. That means we're working out 2 and 5% from the tables. One more time, let's check what it is. So degrees of freedom 2, 5% is 5.991. So that's what we're going to be comparing our calculated one with. So this time around, I'm glad this happened. The calculated one is less than the critical one. What does that mean? Not enough evidence to reject H naught. So we accept H naught. What does that mean? The distribution we proposed at the beginning, so that means binomial 6, 0.4 is a good distribution for this model. It's a good model for this particular data. Right, so now we move on to the second type of question when we're testing the associativity between two things. Okay, so state your H naught and H1. These are steps. I'll go over the steps once and we do the question together. And H naught is always, this is standard once again, guys. H naught is always, there's no association. H1 is, there is association not independent. Then very important, guys, you have to memorize this formula, calculate the expected frequency like this, and then combine the columns. I would like you to note down this formula in a book so that we can move on. And then combine the columns. This is very rare in this type of question. Okay, calculate degrees of freedom. This is really important. Again, second formula, memorize this, write them in the book right now before you move on to the next part of the video. Number of rows, take away 1, number of columns, take away 1, times them together. Find chi-square critical value from the table, calculate the chi-square, same method, and then compare and conclude. Okay, so guys, we're going to be doing a question based on this now. And the question we're doing is question number 9 of exercise 6E. So guys, have a look at this question carefully, copy this table, then we'll work on it in the next part of the video. All right, people, the scientist wants to find out if there's an association between the gender of the organisms and the beach type. Okay, so what do we say? H naught is always standard. There is no association. And H1 is that there is an association. What does that mean in this case? Because association means what? That the gender is connected to which type of beach they're talking about. No association means gender is not connected to that. All right, guys, so this is our observed data. This is the observed data here, guys. What do we need to do after that? We need it to be working out, guys. What's good? This is the choice of beach and the gender we are trying to find if there's association or not. Right, so what do we do now, people? We work out the expected frequency. So expected frequency for each row, each cell of this table is row total times column total of that cell and divide by the grand total. So guys, it's advisable to work out these totals first, okay, of each row and each column. So after working out the row and the column total for each row and each column and the grand total, guys, we're going to be starting to work out the expected frequency of each cell. For this one, A of male would become, so A of male would become row total. Row total is 166 times by the column total 100 divided by the grand total 500, and that comes out as what? 166. This comes out, let's work it out, guys. This comes out as 33.2. So this is 33.2. Similarly, for this one, I do what? 200 times 166 divided by 500. So which, because this is only difference is 100 to 200, will be double, I think, 66.4. Can you all work out all the other ones as well for me, please? Thank you. Guys, once we work out the expected frequency, nothing changes after that. We work out the, see if the expected frequency is less than 5 for any of this, or I told you it won't happen, okay? And then we're going to be working out the test statistic, guys. Same method. You're going to do expected, so 33.2 minus 46 whole squared over 33.2 for that cell. So plus 66.4 minus 80 whole squared over 66.4 and so on. So there'll be 1, 2, 3, 4, 5, 6 numbers. Guys, can you work that out and work out the test statistic for me, please? Thank you. Okay, guys, my calculations on a different piece of paper was worked out as 27.2676. So what's my next step after that, people? I have to work out the critical value. So chi-square crit, I will work out as chi-square. I need to work out the degrees of freedom, and significance level in the question was 5%. So guys, degrees of freedom, then the nu is the symbol. This is the formula in this one is very simple. This is R minus 1 times C minus 1. So 1, 2 rows, 2 minus 1 is 1. So it's 1 times 3 columns, 3 minus 1 is 2. So degrees of freedom is 2. So we're going to work out 5% significance level, 2 degrees of freedom. And I think we did that last question as well. This is 5.991. So 5.991. And guys, what do we do after that? We compare this critical value with the observed value which we got. So guys, what happens here, that your observed value, calculated value is bigger than the critical region. That means what? Enough evidence to reject H naught. So this is reject H naught. What does that mean, people? Yes, there is an association. That means the association means what? The gender will be dependent on the beach type. Okay, so that means they're not independent of each other. Okay, so this is the associativity question. All right, guys, the last question I would like to do in this is I've gone back into goodness of it again, because that's slightly trickier. This one, you know, associativity is not that tricky. So this is question number 9 of exercise 6D, I think it is. So guys, have a look at this question and we'll work together. Okay, I'll give you a couple of minutes to look at the question carefully, pause recording, then we see how do we work that out. Right, so this is really a nice question here, because can you see it tells me it's binomial, okay? And in the question, guys, if you want to go back and check, it tells you it's, can you see it tells you it's binomial, and it tells you both the parameters. That means you're not calculating P this time, okay? So degrees of freedom will be just the number of columns left in the end, take away 1, okay? Right, tells you it's binomial. So guys, it's given you expected frequency of quite a lot of these things as well, okay? But we've been asked to find the expected frequency of 3 of them. So guys, how would you do that? First, expected frequency is you want to work out probability that x equals 3 with that binomial model, then times that by the total of the frequencies. And the total frequencies here is 200, I think, okay? So times that by 200. I think this is 200. This is how we find expected frequency, guys, isn't it? We find the probability, the times by how many times that thing has been happened. Can you please work out R, S, and T now? Thank you. Okay, so using binomial PD, I got 0.2187 something as the probability times by 200, about 43.75 as the value of R. Let's work out value of S and T as well. Right, guys, what do we need to do now after calculating the expected frequency? I want to see if any expected frequency is less than 5. We need to combine the columns. So this is less than 5. If I combine this with the next one, it will make bigger than 5. Yes, it's right. So this is, we're going to combine these two, and same on the other end as well. Okay, all the other ones are same. So guys, what do we need to do? We need to make the new table now, and then degrees of freedom, then find the critical value, find the calculated value using that same method, and then compare and conclude. All right, this is the new table. So once again, guys, be very, very sure that you add the observed frequencies as well when you combine the columns. 9 add 1 gives me 10, and same thing over there as well. 5 add 2 gives me 7. And then obviously, so guys, what do we need to do? We have to calculate the test statistic. And first of all, degrees of freedom here would be 1, 2, 3, 4, 5, 6, 7. So it'll be 7 minus 1, which is 6. I'm not doing that extra minus 1 because we have not calculated the parameter. It was given to me. Okay, and significance level of the test, and then work out the critical value. Significance level was 5, so 5% of 6. The answer from the table is 12.592, I think. Okay, you can check that. Then calculate, guys, calculation. How would you do that calculation? Same thing. It will be 10 take away 7.603 whole square divided by 7.03 plus 27 take away 21.88 whole square over 21.88, and so on. We do it for all the columns, and then we work it out. So guys, the calculated one comes out about 5.685. So this is my calculated is less than the critical. That means I can accept H naught. Okay. What does that mean? That binomial distribution 8, 0.5 is a good model. Guys, with that, we've finished this video. All the types of questions have been covered, and I hope it helps. Thank you very much.